this is the answer, you know. So you may not like shrinkage and creep and all this depends on many things, but they don't consider all of them necessarily, not always. Some of them are just, in fact, come to think of pre-stress losses, there are numbers given to you already. Between 25,000 to 50,000 pounds per square inch is the typical loss in pre-stress, right? And they're not even talking about what strength concrete you have, what's the relative humidity, how long it has been. They just tell you this is the value. So one good thing about that is if you're calculating if you're doing your exam or test or something and you find your calculation gives you a pre-stress loss of 5,000 psi, then something is wrong, because those things are not out of, these are limits. They give you limits between 20,000 to 45,000. So your results should be in that range or close to it. If it is not in the range, then there should be a good reason to be outside of the range the umbrella organization gives you, like Prestressed Concrete Institute, ASHTO. These are the umbrella organizations that give these numbers as a preliminary numbers to start with. So if you're planning something, you can start with that. For practicing engineer, that's a very handy tool. And it's a good tool for checking the sanity of your answer. Are you really out of line or something? Because this happens, especially with these large number crunching and people who have not got much of any experience. It may sound like, okay, so what if I got 150,000 PSI loss? The problem is you're so out of range, you better explain what went wrong, and go back and check. Or if you're starting out in business and you're doing some calculations, nobody has checked it yet, you do your self-check, because you'll be embarrassed otherwise, you did something very silly, right? It is always the procedure in offices. When you run numbers, there is a person who is tracking you. Because we are all human beings, we make errors. So to make sure that bridge doesn't fall down or something, there is a procedure, standard procedure in every office. How far you go to check somebody's work. Because you don't want to take even 10% chance, even though sometimes, depending on your experience, it could be more than 10%. But even at my stage, I don't take that chance. I'll give you an example, and some of you might have heard this one. So I was calculating the number of railroad ties, right? Those of you in my class before might have heard this, but it's worth repeating. So I said, okay, so my railroad track is 1 mile long, and these ties come every 22 inches apart in one standard anyway. So I said, okay, so first thing you find out is how much of rail you need, right, for 1 mile. So you find in terms of how many yards of the rail section, which looks like an eye, like a mushroomed eye. So how long is it? So it came out to be 10,000 linear feet. So then I said, okay, so 10,000 linear feet, now I'm going to find out how many ties I need. So take the 10,000, multiply by inches, by 10,000 times 12, so 120,000, divide that by 22, because that's how much the spacing is. So I got my tie numbers, then I just sent it. I said, what is there to check? I just went around the procedure. In fact, many times, some of who are experienced, I was new, honestly, just 6 months of practice. So the procedure was that if you have any engineering calculation, this was not quite engineering. It was like basic geometry, So I just, okay, I sent it. I said, this is not engineering. Send it over. So I sent it over to the client. And after, how this is one of the natures, it becomes a second nature after you practice for many years, that not worry, but you keep thinking, did I do it right? Did I do it right? So my rule of thumb is, those of you who have been in FEA class, is that do a sanity check. Make sure, in FEA class especially, because in FEA class you have, you get answer for difficult questions that are not in a standard book. So you're analyzing a structure that is very unusual possibly, and nobody knows the answer. So what you're going to do? You're going to running a model, actually, mathematical model, and you're getting some results. And how do you believe that? So like we talked in the other class, you do some simplifications. You assume the support to be simple support, the load to be uniform, the cross section to be this and that, and you come up with a number that should be, half or double of what you get now. If you get your results to be 10 times different, then you can say, well, something could be very wrong here. Right? But that's not the case here. Here we have guidelines. The PCI and ASTRO will tell you that your losses are within this range, right? So you check it out. So anyway, long story short, on my railroad ties, I sent it over, and because we become, after a practice of a few years, it becomes second nature, but me, I started early on. Maybe I had done a PhD, so I was skeptical of my knowledge, or maybe, PhD is one of the humbling experience, because now you know what you don't know, because you've gone through a lot, and you have gone to the depths of some of the items, and you say, oh my God, I think that great scientist, Newton was it? He said, we are just sitting on the seesaw counting pebbles, or something, like we are such a silly thing we are doing. We don't know much, So, so I said, no, I better check it. So I checked, and I found out I got twice as many ties, because I didn't divide the length of the track. I divided the 22 on the bottom for the length of the rail, which is double the value, right? Two rails for one track. So I had twice as many, about a couple of thousand more ties, basically. So that was a lot of ties. Where is it going to store it even? Forget, waste of money. So I called immediately. Guy said, oh, I was about to push the button. I said, okay, just stop. So what I'm trying to say, you don't want to put yourself into that situation when you're practicing, because it has financial consequences. So you will have a hard time explaining, and somebody's going to incur a lot of loss somewhere, and nobody will like that. So maybe your job loss, even if it is really that bad. But that's why even if nobody says, no, that's okay, just go ahead and send, I don't do it, I give it to somebody, please check it. So the moral of the story is that your book has those standard numbers. So you're running your assignment or your test, look at it, see if you are in the ballpark, right? And also, the other reason these are given is, we may be thinking that pre-stress losses are exact number like a mathematical calculation, and we will get it pretty good, because these are formula that have been derived or have been reached from statistical analysis, data fitting. They should be within 2-3% or 5% maybe, but that's not the case. It's a whole lot, inaccurate, if you will. If you are within 10%, you're doing really good, because there are several factors, and each one of them, like if you going back to surveying, there are sources of errors, and they add up, if you keep doing it for a while. So things add up in 5 factors. Each one is 2% or 3% contribution. By the time you do 5, you may be 15% off. But that's not bad for what we are doing, because we have so many factors and so many, the type of aggregate, the humidity variation, so many things. So our material is not well behaved like structural steel would be. So that's why you need to watch out, right? So long story short, practice number 1 for the test. In other words, you don't just look at the book, read through, and okay, I understood. You all know this, but just to remind you, going back to the first calculus class, I almost flunked it because I just looked at the answer, and I said, I understand what this is, but in the test, you're just totally blank. There is no idea what you want to do. This is like that. It is not very complicated, what we are discussing here. Not very complicated in the sense of the rigor of mathematics is not there. What is complicating is that we need to understand our material. What's the personality of our material? What is it sensitive to? And it's not one material, it's a composite material. There is aggregate, there is cement paste, there is sand, there is rebars, there is pre-stressed bars, and so many things. Then how much you cure and how long you cure, so many. And what's the humidity, and there are so many factors, dozen factors. So you need to understand what affects. So that's the trick. You understand the material, you will get it, because the equations are all there, and they're not very complicated, really, as you have seen in your assignment. What is more important is, do you understand the question and what is being asked, right? Okay, otherwise I don't see why most of us will not get B's in this class. I really don't. But then you have to be on your material part a little more clear on how the phenomena is happening, what is important for this phenomena, right? So let's continue. I'm not going to cover a whole lot. I have been suffering with some cold, but today is a better day. I actually took shower, so I feel slightly better. I was in the site somewhere, so during the day, I had a mess, mud and everything. Somebody has some problem. Now that I have this, your attention, it's such a silly thing in civil world, in civil engineers world, as opposed to architects world or an artist world. You can do so many things to hide your defects. You can, if you're an architect, for example, they may not like to hear this, but if you have something went wrong in your elevation view, looking at a building, you said, oh my God, what did he do here? Or you can put up a tree or a bush, and okay, nobody knows what's behind that, right? Well, in our case, if the beam fails, prestressed concrete, it's going to sag. Everybody will passing through see, even though it's not completely down on the ground. People, what's wrong with this? It just keeps on doing this, or it keeps on doing this, or whatever. In this case, somebody surveyed wrong, so they put the foundation 1 foot 4 inches too high. We have spent $200,000 by now. So now what do we do? So we had to sit there, and how do you minimize the loss? There is going to be problem, obviously. So it was one of those, not shouting match, but who was at fault, number one? Who did this, number one? Nobody's saying that, but it's obvious, It's obvious that they have somebody in mind. And the guy who is in mind, it was there, and he was without anybody saying anything, he said, well, this happens, that happens. And so it was interesting. And then you go around and you look at, and they want the answers now, and what are the repercussions? Because now you have to fix the whole building. The foundation is too high. And if you say, okay, so what's wrong with foundation being too high? The problem is there are other things coming and going out of the building. They all have to be coordinated with the other buildings. So if you raise this one, then what about the pipes that are coming in and out? They have to be at the right place. Your flow has to have a slope. If you're too high, then there will be no flow, because there is no slope now anymore. Anyway, long story short, it's in civil engineering, this is one of the problems. In engineering in general, but especially civil, because here's where we actually meet the mud or dirt. You had to deal with it. All these mechanicals, and anybody's mechanical here? That's all right. I can still criticize for this. But what I'm trying to say is, some of them, well, last time in FEA class we had some those strange characters, they're not civilized. So anyway, just to boost your morale, it's nothing wrong with it. You should feel proud as civil engineers, one of the oldest branch. Well, anyway, so you have to you need to not worry, but you need to be very cautious. Because in a mechanical case, you can modify, you see everything. Our foundation is buried, and if it fails, the whole thing comes down. So you're standing on something, right? So it's interesting. I'm sure when you guys become experienced and mature and all that, you will start enjoying. In the beginning, it is kind of a little rough, People are a little nervous because you don't know you have no feel. I can't tell you how good this table is because I don't have a feel. Some people, they can pick up a fruit and they can tell how good is inside, right? That's from experience. Or in engineering, something like that happens after you practice for a while. You look at something and say, I know something is wrong here. Without even knowing what the heck is wrong, because of experience does that. So then once you have that takes about 10 years, sometimes 15 years. Then you start having some confidence that I think I know what I'm doing. So the more you learn, the quicker you learn. And I think going to graduate school is one of the ways to be a quicker learner, because you have gone through some more rigorous exercises, compared to the undergraduate. So I think that's a good thing you guys have all decided. But anyway, I'm going too far, so let's see what we are going to cover. So we are going to look at the prestress loss, right? So prestress loss, there are short-term losses and there are long-term losses. We have talked about that. Short-terms are instantaneous or very quickly happen, almost instantaneous. Long-term will take forever, but practically at least few years, right? It may take 20 years before you say, now I know relaxation is done and creep is done and shrinkage is done. But the other kind, which is elastic shortening and the anchorage loss and friction loss. And depending on the type of pre-stress, you may have different kinds of losses. If you have pre-tensioning, then you have one kind of losses. If you have post-tensioning, then you have those losses plus some more, right? So post-tensioning has more variety, in other words. Pre-tension, you have less variety. Right? And we'll talk about, that's where we will start actually. And I'm kind of abbreviated here, like I said. Let's see. So we'll look at the PowerPoint first, which is abbreviated version of the chapter 3, not all of it. We'll cover about 30 to 35%, 1/3 maybe, or maybe 40% at the most. That's what we will cover in about 5 slides or something. So let's go over somewhere where we left here. So this is where we need to start. This is where I left. Okay. So I am going to, let's see, I think is it view or is it slides? Okay. So let's, I'm going to dwell on this for 5 to 10 minutes, so just bear with me. There's a lot of stuff here. So 2 categories, that's the easy part. There's immediate loss and there's time-dependent loss. Immediate is elastic shortening, and I've talked about that. You just suddenly shrink the length. And anchorage loss is as you seat your wedges into the ends of the beam, you're losing something, right? So there is this, the time-dependent losses, creep, shrinkage, and because of the nature of our material, that long-term behavior of material. So you may take 5 years or even longer before you end up having the stabilized value, right? Typically 5 years is practically done. You know, that's what you normally do. 5 year calculate, 90% done at least. Anyway, so exact value is not practical, not required. The reason being that we are working in the, not in the LRFD design, if you will. We are working with service loads, not factor loads, right? So there is a capacity beyond us that we are not considering yet. So it's not a big deal that you lost it. What will happen, worst case, is that you may start sagging if you get too much losses, right? But it's not a threatening, it's not one of those where it will fail or something. So that's why approximation is okay. And as you will see when you have done your assignment, that it's not like you've got to be exact. You know, if you are within the range, then you will say, okay, I'm good, I don't need to worry. That's why. And then it's not practical because in order to find accurately, there is a lot of interaction between the things. Like relaxation, the loss of relaxation depends on the stress applied, right? So as you lose stresses, the relaxation loss assumes that your initial stress is going to stay, right? Well, it's not only losing stress because of relaxation from beginning to end, it's also losing because of the other phenomena which we are going parallel, which is the shrinkage and the creep are also losing. Your pre-stress is lost. So the less the stress you have in your pre-stress steel, the less the relaxation, right? If you stretch something very hard, then it will tend to relax more. It's like creep. So what we are saying is, but the way we calculate is as if they are independent phenomena, you see. One doesn't affect the other. Right? For example, shrinkage affects creep because it's shrunk already, so creep will not be, stress has gone down, so creep will be less. But we don't do that. We just assume the initial stress. In other words, we are overestimating. You with me? We are overestimating because we are not considering the decay in the available stress in the pre-stress trend or in concrete. We assume that to be constant throughout, even though we know fully well the other factors are, and the factor we are considering is going to bring it down, right? So it's not practical, or you will be doing it every week. Like, I want to know what happened in the first week. At the end of first week, I know my stresses. So for the second week, I will start with the end of first week stresses. So suppose you started with 200 KSI as your stress in your steel, and after a week it is 190 KSI. Well, there is a difference, but if you kept on doing that, you will have to do it for weekly basis. In other words, you have to do it 100 times over for 5 years, right? Hundreds of times, really. So to avoid that and to keep it simple, there are practical formulas that kind of tones it down based on the actual results, right? So you don't have to worry about doing it in a weekly or daily basis, because that will be more accurate, right? Anyway, it's like FEA, really, how you need to be practical, right? So engineers are to be practical. Anyway, so like I said, to be sure, this third part, for routine designs and for average conditions and for preliminary checks of what you should be selecting, there are values in table 3.1 and 3.2, which we'll look at in a minute. I'm just going through this. Look at those numbers and see what's interesting about them. So we keep those ready to go. In pre-tension members, because they have only 4 kinds of losses that are of concern. 1, 2, 3, 4. These are the 4 kinds of losses for a pre-tension member. And you remember pre-tension member is the one where you have cast the concrete around your pre-stressing wires or bars or strands, right? It's bonded together with the other material. It's in contact with it, right? It's not through the duct. And you, within a day or 2 or 3, you cut the ends, umbilical cord, if you will, and you make your shipment, right? So that's the kind we are talking has less. But why would you do this? Because this is good for mass production, otherwise it's not that good, right? So, and you need a whole lot of more skill here and more hardware here than here, so you need both. So in this case, the losses, the number of losses are less. Doesn't mean the amount of loss is less, it's the variety of losses, right? So the first one is called the delta means the change, F means stress, and P for pre-stress, and ES, which is uppercase for elastic shortening, right? So this is like a formula. If you forget what the heck it is, then delta means the change, of course, right? In our case, the change is the loss. F is for stress, P for pre-stress loss, and ES for elastic shortening. So once you know this nomenclature, then same thing, delta F, P, R for relaxation, right? And then delta F, P, CR for creep, and delta F, P, common, SH for shrinkage, right? So we know these are the 4 factors that we should be looking for. If somebody says, hey, calculate me the pre-stress losses in a pre-tension member, and you start thinking, how many do I have? So you have to remember 4. And then you say, okay, I've done only 3, where is the 4th one? Which one did I forget, right? So that's why you remember these 4 items, and then you add 2 more here. So what are the other? So in this case, this is an example. You don't have to worry about what really happened. We'll go through this a little bit more detail later, but let's see what this says here. Where, for example, this is an example, the loss and relaxation is calculated from T0 to TTR, which is transfer, at the type of transfer, time of transfer, which is a higher value. So you calculate that separately. It may be for 2 or 3 days or 1 day, depending on how you do it. Right? So for those few days, you calculate T0 is 0, obviously, because that's when you stretched it. Then you left it there for a day, then you came and cast the concrete for another 6 hours, and then you waited for next day morning. So that could be 2-3 days here. But those 2-3 days between T0, which is practically 0, to TR, so you put that in. So the relaxation is from there to there plus relaxation from TR to TS, where T0 is 0, jacking, transfer, and stabilized loss, which is 5 years or more, right? So the S for stabilized time. You think that you're good enough. You don't need to go beyond. So that's 43,000 hours versus maybe 50 hours here or something, right? So you need to watch out. The reason for this separation is this is a faster moving, because in the beginning you are losing a lot and the stresses are higher because you haven't lost anything yet. You're just holding it. Then your elastic shortening and creep and shrinkage and all that are happening. So this is generally done like this. That's the other complication in pre-stress loss, is your losses are calculated not only for the entire length, but they can be calculated for intermediate spots if things of this nature happens. Some of the phenomena you don't do, some of them you do, right? So this is a stage. The transfer is one stage where we calculate, right? This is just to improve the accuracy, not gets out of hand, somewhat accurate. Right? Also FPI, which is the stress in pre-stress initial, is equal to FPJ, which is what you stretched it to, right? Minus the delta FPR for relaxation from there to there for the first 2-3 days, minus delta FPES for elastic shortening. So as soon as you cut the bar or the strand, then the concrete material is going to elastically shorten, right, because of the stress. Then you will lose some, right? So you lose some stress. That's why you do it after the transfer. So this minus that is the FPI. That's where your creep and shrinkage is more seriously happening, because not much going on in the beginning. Right? So that's why these are taken out, and this is called what we call FPI. In our initial calculation in chapter 1, for example, that's what we meant by FPI. FPE is at the end of 5 years or more. Right? Okay, so this is clear. Then the next thing is the post-tension members, where you have a duct and you have cables or bars that are going to be tightened at a given time, waiting for longer period. Because you cast the beam somewhere, then you transport it over the top of the abutment, then you have this duct ready to go, then you put your jack, then you pull it. So it takes time, all this takes time. And you don't know how long the beam has been waiting. It may have been cast in a factory somewhere and you bought it. That's possible too, if it is not too big. So it may be weeks and months even, right? So we need to keep that in mind in case of post-tensioning, because the good thing about that is, if you have waited for say 2 months, now you have a stronger material, right? 2 months means it's way beyond your compressive strength that you are 28 days, right? Versus this one where you're applying your stresses already at very lower level, like 50% of 28 day strength, or even less, depending on how you cured it. If you cure with steam, then it is quicker. If you cure with moisture, with water and spray and all that, then it is not as quick. So you have to keep in mind in post-tension. So here we are, in these 4 are still valid, which is the elastic shortening will happen as soon as you release the bar into the wedges, right? And then relaxation also begins right away. And then you have creep and shrinkage. But before all this happens, there is already something going on, anchorage and friction. So we need to understand what that is, right? So before you lose elastic shortening, you have anchorage and friction. This is kind of almost like a sequence. This is first, this is next. Not exactly, but something like this. That's why this is written first and this is written last, because these are really long term. These 3 are actually, right? So it's shorter duration is here and longer is here. But anyway, so this is in sequence, anchorage happens first, in other words. So how does that happen? You're stretching the wire, and then as you relax, there are wedges gripping the wire, and the grip happens because of the shape of the body at the end is conical. So you have a cone, and you have a piece, 3-part cone inside a cone, right? And so as you pull in, the one that is gripping the bar now is seated. But it takes a little bit of loss before it gets really, before the thread on the inside bites into it. Look up some websites, they'll show you even more details of this, where the material you use for wedges is harder. You know, like when you cut glass or any material, the knife has to be a harder, right? Harder value, or it will not cut. If the knife is made out of aluminum and you're trying to cut steel, it won't work, right? So our wedge material has to be hardened, extra hard. So it will grip and indent on the top of the cables and the bars. It should feel like you are trying to grip a piece of wood. Not exactly that exaggerated. So if you had a wood and you put steel wedges, then you will be able to grip it, right? Well, we don't have that difference, but we have to enhance the hardness of the wedges compared to steel to have some difference in hardness, right? So, any case, but nothing is perfect. It won't grip right away because you can't make it out of diamonds, obviously, because that will be the hardest, but then it won't be as strong. So, any case, long story short, there is some loss because it takes a bite, takes a little longer, and it loses something. So that's where it is. This other one is the friction loss. So as you stretch this inside a duct, you have a duct like this, depending on how many spans you have, and you're pulling it at the end. Well, the cables or the strings, or what you want to call it, the wires or the strands and the wires, the braided wires in other words, are going to rub against the inside of the duct depending on the material. If the duct is lubricated, or if the duct is made out of Teflon lined, right? So that the friction, if you remember, the friction is a function of normal force and the type of material. So we are putting a lot, as you go through this shape and you try to stretch, you're going to push against it. So there is a normal force. And depending on the texture of the material, how rough it is, you will get bigger and bigger friction. So you're pulling something and the friction points, the extreme points, top and bottom, are going to say, no, you're going to drag here, so I'm going to reduce you. So in other words, you got 100 kips here, 100,000 pounds. As you go inward, you're going to lose some more, and some more, and some more. And there are procedures where you're pulling only on one side, not the other side, because the other side is blind. So you're pulling on one side, now you got maximum loss on the opposite end, right? So depending on whether you have two jacks, you're pulling like this, or simply like this, you will have your losses more and more, right? So in case of both sides pulling, the worst case is right in the middle. When you are pulling on one side, the most loss is on the other opposite end, right? Make sense? Okay. So that's the friction loss, and then these are exactly the same phenomena, right? Which is elastic shortening. The only thing, just to be sure, like last time we talked about this, elastic shortening. So if you pull and you allow it to go into the wedges, now at that point, the force, if you are doing it all together in one stretch, all wires and all strands, then there is no loss because they're going together. Well, if you do it the other way, where you're doing pull one at a time, then what happens is the first wire that you pulled, or first strand you pulled, is going to say, okay, I have not lost anything till you start pulling the second one. Then you're going to shorten the beam some more. Right? At that point, you can lose a little bit. You pull the third one, then the first one lose double, and the second one lose only one time, and so on. So in the end, the last one doesn't lose anything if you do one at a time, because it has nothing to follow, right? But all the others will lose, right? So if you have 10 strands, then the ninth will lose a little bit, but the first one will lose the most, right? So works out because of beautiful mathematics, like our president says. Anything powerful is beautiful for us. He said, beautiful. Well, whatever. He's got very special adjectives, but anyway. So that's not appropriate here, but it works out very elegantly. That's the right word, really. Mathematics, that's one good thing about math is things are elegant. If you know calculus, it's elegant because all of a sudden something that looked very difficult to calculate, like the volume of a serving cup for drink, it's difficult to calculate those shapes and all that, but if you revolve it about the vertical axis, you can calculate very easily, right? Area revolve around the vertical axis. So it's elegant, right? So this becomes elegant in the sense that your loss is half if you pull it one at a time, right? You pull it together, no loss. So elastic shortening loss for post-tensioning is special case. You may or may not have it, right? Depending on how you stretch it. So you may have half. So it can be half of this or no, nothing, right? So it's not as bad in other words. And relaxation, of course, starts kind of late. And all these start late. So just the difference is that the shrinkage and creep has already happened before you applied any stress. So those things, and if you waited long enough, like a month or two, then hey, most of this is done anyway, right? More than half. So you have to watch out where you start, right? What strength you start. Okay. So let's see, this is the most important part. this is, I would say, you should think about this, you should read the book a little more, because this is just something like 2 or 3 pages. So I just thought, if you can remember this particular page, then and try to understand every part of it, the rest is all detail. It's really just use the formula and all that. Problem happens when you don't study this and you start applying formula. You're on the wrong formula, or you have the wrong time or something. So watch out this. Okay. Where are we on time then? So pre-tension elements. So we're going to start with we're going to cover only 3 or 4 kinds of this, right? Or not all kinds of stress losses. So let's talk about elastic shortening concrete of pre-tension members. So here's, just to repeat, I guess I have already talked about this, but the strain, as you apply the stress on the concrete, you have an average stress. And because of that average stress, you have an average strain. Or you started with a 100-foot long wire and it became 99.9 foot long. So you lost something, 1% or 2% or 3%. You could, because these things are very mild and they are not brittle, so you can stretch quite a bit. As you saw in the video, you can measure it like 6 inches. You lost 6 inches. Pull the ram 6 inches. You elongate it by 6 inches, right? So you pull that, now you release the pressure on the concrete, right, one way or the other. So the concrete sees the pressure, so it shortens in length accordingly, right, because of the pressure. And that shortening is also shortening the strand. So for example, the concrete beam that was 100 foot long became 90 foot, 99 foot and 6 inches, suppose. Then that 6-inch shortening of the length of the beam is also shortening the length of your pre-stressing strand or bar or wire, right? So if you take a wire and you apply a force, then you shorten it, even without, because the force is already gone by then, right? Shortening it, it will lose, right? It won't have the tension you started with. So if you have a wire stretch between these 2 walls, and I move this wall 6 inches, the stretch you had, the tension you had in the wire is now accordingly lost. And how would you calculate that? You say 6 inches divided by the length of this room, right? That is your strain. Then you can calculate this is loss of strain, right? So strain and stresses are directly related by elastic modulus. So you can calculate the loss that has changed, or loss of stress. Loss of strain, loss of stress are directly related linear elastically most of the time. So any case, so your strain in terms of stress, the strain in concrete due to elastic shortening, let's call that EES, which is delta ES, or change in length divided by the original length. That's the strain your concrete has gone through. Then you can say also in terms of stress, you can say the strain is this ES, which was here, is actually related to FC. So you take the EC on the other side and you can calculate the stress in your concrete, right? Okay, so once you do that, then you can do strain compatibility, because the 2 members are working together, or 2 materials are working together. The strain has to match, because one strain is the same, the other one, because their lengths are same, the displacements are same, so strains are same. So the stresses will be same? No. Strains are less same, but the stresses will be different.
Yes.
Because the elastic modulus is different, right? This is like any other composite material. If you're working with wood, and if you have a plate, steel plate and wood, and you shorten this or elongate this, then the stresses will be different, because the elastic, you're just making the same strain, right? Your strain is same, but because of the difference in elastic modulus, the stresses will be different. The strain is same, stresses are different. So what we have to do is you have to say the strain in pre-stress is equal to the strain in the concrete, so which is ES, like we calculated up there on the first line. So that's the same ES, right? Multiplied by the Young's modulus of steel, that will be our loss, right? So our modulus will be the steel modulus, but the strain is already given by the concrete, right? How much and the strain in the concrete depends on how much pressure you apply on concrete, which is the force you apply divided by the cross-sectional area if it is concentric. If it is not concentric, then it gets more complicated, right? But simple example is concentric, right? So any case, so this ES times the strain ES, elastic shortening of concrete, gives you this loss. Then you can now write ES PI over AC, which is if it is concentric, the initial pre-stress divided by area, multiplied by EC, right? So that's how you'll get your stress, or strain rather. This is stress, this is EC. So stress and EC and strain in concrete are connected, right? That's what we are doing, sorry.
What does ES mean?
Elastic shortening of concrete,
Oh.
ES. Remember we talked about ES, elastic shortening?
Yeah.
Yeah. So the strain ES, we didn't write concrete because elastic shortening is same for both material, right? That's why we didn't write ESC or CES or nothing. Just strain ES, because that strain is common to both concrete and steel. That's straining the same. The length is same, the displacement is same, strain is same, right? Is that, am I making sense to you? I was not pointing towards you necessarily, but I want to make sure everybody is here. I don't want to go too far because this is the crux of the matter, really is. Because if you are skipping this one or you don't follow this, then the formulas will go astray. In other words, you will use wrong formula. So, I'm sorry.
Well, what's the difference between the ES and the ES?
Oh, this ES
Yeah.
and this ES.
Yeah.
This is a subscript. This is the main character,
Yeah.
the Greek E.
Yeah.
This symbol is for strain.
Strain.
Anytime you see this Greek symbol E,
Oh.
then it represents strain of some kind, right?
And what is the left
The
ES?
one here is the Young's modulus, E, for steel, S,
Oh, still. Okay.
right? So E is Young's modulus, S for steel, right?
Okay.
If you see EC somewhere, which is right here, then this is Young's modulus for concrete, right? So that's, watch out what you're using here, EC or ES, right? So here, well then if you take the ratio of these two, it becomes ES divided by EC, just moving around the symbols basically, right? Just to look elegant, right? So in mathematical terms, so look nice. So because NFC, this ratio, N is a ratio of ES to EC, which is a commonly used name for the ratio. It's called ratio, elastic ratio. It's the ratio of the Young's modulus of steel divided by concrete. Usually comes out to be 6 to 10. Those of you who have done concrete, you must have come through this, especially composite design, where you have steel beam and a concrete slab on top. You have to use this. You have to have elastic modular ratio or elastic.
It's a standard value.
No, it depends. No, it's not standard because even though the elastic modulus of steel is constant, pretty much constant, you will see slight variation in elastic modulus of steel because the strands are braided, right? The wires are not braided. So the wires are pure. The braided wires or strands are not pure. When you stretch them, they're a little bit softer because they have been braided. They're not straight, right? So that's why the ES for strand is 27 times e to the power 6, and ES for wire and other things is 29. So there is slight difference because of the shape, right? Otherwise, that ES is always same number, 27 or 29, not much different. But the concrete is complicated because concrete depends on, there is a formula, 57,000 times square root of F prime sub C and all that. And depending on the water cement ratio, there is a more complicated ratio, depending on what you got, right? So depending on the strength, there are different formulas. So you watch out how you calculate EC, right? And we'll guide through this, the book has several expressions to make sure you don't follow the wrong, but it is not constant. It is a function of the strength. So it actually increases as time goes by. You see what I'm saying? Because the strength of concrete is not constant, so the EC is not constant. Plus, the concrete EC is not same, or strength is not same anyway. So it has got, and it is related, in steel, the modulus is not dependent on the strength. No matter what steel you pick, it's practically same. Whether you have high strength, low strength, doesn't matter. When concrete is different, depending on the strength, the EC will go up, 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 up. More strong, more EC. Right? The slope of the stress strain curve is steeper if you have a high strength concrete compared to a low strength. Right? So the low strength is flatter like this. So the slope of the initial part of the stress strain curve is drooping down. So that's why the EC is complicated somewhat. Right? So the ratio is not a constant at all. It varies between as low as 5, as high as 11 or 12. It's not a huge difference, but it could be easily doubled. Right? Okay. So anyway, back on this. So the elastic shortening loss is N times FCS. It's not very complicated, is it? Well, you need to know, understand the phenomena. That's the problem. The formula is not complicated. When does it happen? Why does it happen? And what is the mechanism of this? Why does it happen, and what extent, and strain compatibility? This is pretty well compact written, but book has a little more explanation. So then the FCS, or concrete stress, for non-concentric, which is most of the time, your pre-stress is either bottom or top depending on where you are, right? So then you can write the formula we had for the assignment, which is PI over AC times this plus the dead load. This is the self-weight stress in concrete at CG of steel. Why we had this? Because like the video showed, the dead weight of the concrete applies right away as soon as you do this. Right? It cambers up and then cambers down a little bit and stays cambered up slightly. So the weight is applied whether you like it or not. Even if you are sitting on a flat floor, it will camber up and do this like one of those yoga curvatures, like where you were trying to hold this and curve the middle part of the body, right? So that's what it does. Right?
Why there is above the FCS?
Which one now?
NFCS.
Oh, this one?
Yeah, why there is a
Comma?
Yeah, comma.
Oh, that's just me trying to be more grammatically correct.
Oh.
Yeah, this is not the end of the sentence. That's what, I can take it out easily, no problem. No big deal there. Comma is not part of that. Comma is just a pause as if it's not completely done.
Oh.
All right, so that means this expression, I'm explaining the various terms. So FCS is stress in concrete at center of gravity of pre-stressing steel. So that's what we want to do, right? And then if it is concentric, it doesn't matter a whole lot, but then otherwise you use this formula, right? And then where MD is the self-weight moment of the beam itself. Because that's already there, because the other loads will come later. So when we are looking at elastic shortening, this one is already there. Right? That's the whole point. And the reason I'm going through all this is sometimes we forget that, right? You will say, okay, elastic shortening, what load do I have to use? You forget the MV. You don't use this because you're not thinking the phenomena-wise, what's going, how it works, right? So you need to have that clear in your head so that you don't have to scratch your head and think, what should I do? You know, so you just feel, it comes with some thought and spending some time. So anyway, post-tensioning elements. So that, like I was saying, in elastic shortening for post-tensioning beams varies from 0 if all strands are jacked simultaneously to half that value for pre-tension case. Just like what you calculated up here, you take half of that if you're doing sequentially one at a time. Right? Okay? Ahmed, you're here, you're reading stories or something? You're okay? You're okay?
Yes, but I have a...
No, sorry.
Yeah,
You fine? You have a headache?
yeah, a little bit. But I'm preparing for the exam. Let us
Take a break?
No. About the first part of the exam. Can we do it like in different class? Like the next class at the beginning, 5 minutes, and we make the whole class for the solution part? Because I think the solution is not gonna take, it's not gonna be short part.
solution of what these problems?
The second part of the exam, let us make it on the whole class, and the first part we do it like the quiz.
Yeah.
Like
the first part is like
not in the same class, not in the same lecture.
Oh, you want to do it 2 lectures?
Yes, that for 10 minutes, but we make the whole lecture for the solution, because I'm thinking between these files and where we should look for each question. You know what I mean? It's a lot.
Yeah.
Let me think what you're saying. Let me get
Try
some
this.
more.
Yeah.
Yeah,
I
don't
struggle
be
to
puzzled.
work it out.
I gave one extra time because I realized that it's not fair. You guys had some tests this week, so I thought it would be too much. And one of you was not going to be here for sure. But then we have to do something. We cannot continue. What I think you're saying is have the quiz only next time.
The solution part is gonna take the whole lecture, because it's. I think it's gonna take lots of time for solving, then checking the numbers, and
It will take me also a lot of time.
Yeah.
So if I think of myself, yes, but it won't be right. Let me think about it.
thank you so much.
Is that bothering you, or you're okay?
No, I'm okay. Thank you so much.
Because you usually look and ask questions. Today I
I'm
saw.
stressed, a little bit stressed.
You're stressed out. For this?
For the exam.
For this exam? Next week?
Yep.
Me
Oh.
too.
No. When you're stressed out, you work harder. That's all there is. Well, I tell you, we are all human beings. We all stress out. I stress out, right? What I do, not that everybody should do this. There are so many ways. Some of them are religious, but forget that. I just get up. I do for half an hour. At my age, what happens is sometimes, and you might have heard from your fathers and mothers, 3 o'clock in the morning, you wake up once or twice a month, sometimes even once in 2 months. You wake up at 4 o'clock and your mind is racing. And where is in your case, you may be thinking exam, but here's I'm thinking my project, my boss. And it just stops. It's like a machine up here. It just can't stop. Or my bill, whatever, or my son's college or high school, whatever. So many things. Once you get married, you will get taste of it. But what I'm saying is it doesn't reduce. This is peanut. You guys
He's
are
married.
kids.
He's married.
Huh?
He's married.
You married?
No.
So anyway, I wanted to wake you up. That's all my point is. I don't want to take too much of your time and drag you like this. But my short answer is one thing, honestly, seriously, if you're stressed out, you either work hard. Hard work means get up and start doing things. Or the other is go and do some physical exercise. Honestly, it may seem like, what the heck what's the relationship? What I do is I go and swim.
Swim?
Yeah. Or do something, just do some physical exercise. It works. It
You're
really
right.
does.
You're right.
So think about that. Really, seriously. The rest is, all up to, you can pray and all that, but that depends on faith and all, how much some people don't. They don't matter to them.
We're just afraid that we spend a lot of time and do a lot for preparing the exam, but we got the low score.
You take a lot of time to prepare for the exam.
Yeah, we just,
You already done one quiz, which is part of this exam. You've done an assignment, which is still part of this exam, right? So if you've done those two, then chapter 1 is practically done. Chapter 2 is the only to make it easy for you, and we may take a break in a few minutes anyway. So the second part, chapter 2 is the only thing that is substantially not done, right? And chapter 3, we are not going to cover a whole lot. Like I said, 1/3 of it is chapter 3.
So basically, it's chapter 2.
Chapter 2 is the new part. Chapter 3 is an application of Chapter 3 is application of chapter 2.
Yeah.
What we studied in terms of shrinkage and creep and relaxation.
Like, ES is type for elastic shock to complete or elongation.
E is the elastic modulus. Where is which one are we talking? E, this one?
Yes, sir.
E?
Yeah.
This is elastic modulus, a big E. See, this E is the Greek E. This is strain. This is modulus.
Because this E once I have read like elongation strength, so.
No. This is the elastic modulus in this book.
Okay.
So that we don't get confused. You may have seen this in different contexts, But in our context, in this textbook, in general also, E is usually elastic modulus, Young's modulus.
Okay.
So like she was asking, E is for elastic modulus, the little s tells you what it is for, which material. Okay, so which is steel in this case. This ES is.
ES is for elastic shortening of.
No, now elastic shortening is this right here, this ES.
Oh, this ES, okay.
This is a subscript.
Okay.
It's in a smaller size, lower at the bottom. You see what I'm saying? This ES is not
Oh,
at
yeah.
this.
I got it now.
This is down, pushed
Okay,
down. Right?
yes.
So this is a subscript, elastic
Yeah.
shortening.
Gotcha.
Strain due to elastic shortening, right?
Will the big ES be given in the calculation?
Oh yeah.
Oh, okay.
Yeah, you don't worry about remembering the numbers. What is more important in any class for that matter? Do you understand what is going on physically? Do you understand the physical process? That's the key. Because otherwise the formula.
Yeah, formalize it so we can.
Yeah. The quiz part, for example, will not ask you formula.
Will you ask about the details for the chapter 2?
Yeah, we may ask, like, for example, we may ask, what is the difference in behavior of the regular reinforcing bars and the prestressed steel? What's the difference in behavior? How are they different?
And we write.
And you can make a sketch of the stress strain curve of one and the other and say, hey, this one is.
Curve.
Yeah. You can say whatever in that point. I didn't say you show the curve necessarily, but you can say one is more ductile than the other, and you can say one is higher strength than the other. There are so many differences.
Okay. Because I'm afraid of the language barrier.
Do not worry about that. You have good language. The modern, I tell you what, in the old days, especially coming from China, it was hard to communicate. But you guys, you are beyond my expectation. You are doing fine.
Okay.
Oh yeah. I've been here for more than 30 years. So 30 years ago when I met Chinese scholar or student, they were hardly able to talk. Not in a single word even. They will just say yes, yes, no, yes, no. That's it. And food and water, that's it. So you guys have come along and long. And India also, India didn't have that much problem, Indians. And even, for example, Ugandan, because of British background, they were able to communicate better anyway. But these days, my God, these kids, I can't even tell. They still have accent when you come from India, but the language has improved. Then when I came, we were struggling some more, even back then, even coming from India. So.
Like the quiz this week we take from the Dr. Salamia. I see some words, some sentence that I cannot understand.
Well, you should ask. The reason is we don't want you to feel although it is a requirement that you come here, you got to have a minimum comprehension.
Yeah.
A minimum. That way you can understand. But if you still have difficulty, I would not hesitate. I will just stand up and say, could you please explain to me?
Okay.
That should not be the case where you are stuck in the grammar or something. You should not.
Yeah.
No, we are not testing English here. We are testing how much you know.
Because usually he changed the way to explain the same sentence.
If you have question, I think somebody owes you explanation. Anyway, I'll be right back. Since people have taken their breaks. Okay, but I